All right, welcome to Doozer Shop. I got something for you on the whiteboard today. What I'm doing is I've got a machine, I've got a grinder that requires 575 volts, three-phase. Now, of course, I don't have 575. I've got 240 three-phase. Got a rotary phase converter, standard residential area, 240 volts. So at least I got the phase converter to make the three-phase. But this machine's 575 volts. You cannot change the motor. There's no taps, no wires coming out. There's 3 wires. There's not 9, there's not 12, there's not anything other than 3 wires, and it's 575. That's the way it was bought when it was new. Okay, can't change it. So there's been some discussion on different forums. I looked on Practical Machinist Electrical Forum, and you know, there's lots of advice out there. Lots of bad advice from guys that proclaim to be experts. Whatever. I've come up with a way to make 575 using 3 control transformers. Now, what's a control transformer? A control transformer is a small transformer, you know, kind of small, half the size of a bread box, let's say. There'll become a time when nobody has a bread box, so that term won't mean anything. But anyways, like a bag of sugar, about the transformer is. And typically when a machine, you know, it's either 480 or 230 three-phase, and they step down the voltage for control circuits like push buttons, which in turn power the contactor relays for the motor starters, and they use a reduced voltage. Used to be 120 volts, popular back in the day. For many years, controls were 120 volts. And then you can take accessories off for a work lamp on your machine. More modern days, it's 24 volts with the push buttons. They don't want you to get shock, you know, whatever. I've never gotten a shock from a push button, whatever. So I've got control transformers. I got 3 of them. I think they're 500 watts a piece. They go by volt amperes, because watts and volt amperes are the same, except one considers the phase angle. Not the phase angle per se, but how in or out of phase the current is with the voltage. Is it purely resistive or is it inductive? So let's just say 500 watts, even though it's VA, volt amperes. Because they're fairly common. 500 VAs, a bigger control transformer. I got them from some tire grinders or something when I worked for Michelin. I don't remember exactly, but so you can wire 3 together, and I chose delta because when you do delta, the voltage of the transformer is what it is. If you use a Y connection, you're going to a star point, and then if you connect 3 things at a star, you're not getting the full voltage. You're getting less, so you have to have transformers rated for less than 240 volts. You know, so I went with a delta connection, which is, you know, triangle. So I can use the regular 240 volts with the 240 primary of a transformer. Okay, now talking about transformers. These transformers can actually they're step-down transformers. They can go up to 575 and step it down to 220 volts or 110 volts. Okay. So you can run transformers in reverse to step up instead of step down. It doesn't matter. Okay? People will tell you details of that and this and efficiencies and, you know, picking the fly poop out of the pepper. You know, you can do it. It doesn't matter. We're not looking for space shuttle efficiency here, or, you know, I don't know, whatever. Space shuttle is probably not that efficient for the amount of fuel it burns for, you know, how heavy it is and where it goes. But anyways, so yes, I could use 3 of these transformers in delta, you know, 1 for each phase, 3, to step up the voltage from 240 to 575. Okay. I'm not going to do that exactly straight up delta and step up transformer. Regular, as you might know them commonly, transformers are isolation transformers, which means the primary and the secondary windings are magnetically coupled. There's no physical connection between the windings of the primary and the secondary. They're isolated. That's why they call them isolation transformers. What type of transformer is it? It's an isolation transformer. Well, there's other transformers. I mean, it's the same transformer, but it's how you wire it, right? There are auto transformers. Now, what an auto transformer is, there's no primary and secondary. It's just one big winding, okay? It still has an iron core. And what you do is you put the current at one part of this auto transformer coil. And you can take off upstream or downstream of that, you know, where you put it, you know, the current coming in. And you can tap off lower or tap off higher to get the voltage you need from the current you have, okay? Those are not isolation transformers. There's no magnetic coupling per se. It's all one winding, right? So the current coming in is the current coming out with the voltage higher or lower, okay? That's an auto transformer. Why would I be talking about auto transformers? Well, if you use an auto transformer compared to a step up or step down isolation transformer, right? If you use an auto transformer to step up or down your voltage, you don't need as big of a transformer. Or to say, a smaller transformer can handle more current if you're using an auto transformer. So that's kind of what I'm doing, because my control transformers are kind of small. My motor, I think, is 1.5 horses, but I want to use these transformers in an auto transformer configuration to get more amps out of them, more usable wattage, or a higher kVA. A higher VA, okay? It's not kilo, it's a small, it's 500 volt amps. It's not thousands of volt amps, volt amperes. Let's just say watts, okay? I know watts is, you know, resistive, but whatever. So I'm using these 3 control transformers. When I say control transformer, it's how it's used. It's not what it is. It's an isolation transformer being used to power control circuits. I know these terms are confusing, but I want to make sure you guys understand the words I'm saying. So these isolation transformers used in a controls or push button motor controls application are isolation transformers, but I'm going to wire them not as a step-up transformer per se. I'm going to wire them in a step-up configuration, but I'm going to wire them as an auto transformer. Okay, so what does that mean? I am going to wire the primary and the secondary of this transformer together. So it's no longer going to be a magnetically isolated transformer. It's going to be an auto transformer. Okay. You can do that. There's guys on the internet that say you cannot do that. I've got textbooks from college that say you can. Whatever. You guys can argue. Doesn't matter. I've done it and it works. Right? So this video is after that it works. So I'm sure that it works. Okay, so if you're wiring the primary to a secondary on an isolation transformer to use it as an auto transformer, and I think I'm saying this right. If not, help me out in the comments. You can wire the coils. Now pay attention. This is about the direction of the windings, okay? And I'm going to pick clockwise as an example. It doesn't matter, but they have to be the same or different. If say your primary and your transformer is clockwise, and your secondary you wire is also clockwise, that's a boost. It increases the voltage. It boosts the voltage, okay? On the other hand, if your primary is clockwise and you wire the secondary counterclockwise, right, backwards from the first, then it's a buck configuration, which means it, instead of boosting the voltage, it bucks the voltage. It lowers the voltage that's going out. Okay. So there's a lot of terms here. Isolation transformer being used as an auto transformer in wired, configured in my case, a boost configuration. Not a buck, but a boost, because I want to step up 240 to 575 volts. Okay. Now, I'm going to show you the board, which I've so skillfully drawn out, and I only have one color magic marker. You may be first seeing the triangle shape, okay? Which, that's delta. Okay, I'm going to explain all this. So here's one transformer. I got some letters here, A. Here's another transformer. I got some letters going on here, B. And then a third transformer and some letters going on there, C. Okay. So what these are the isolation transformers, okay? There's a primary and a secondary. Actually, the one, this is 575. This is actually the primary. How the transformer is sold, this is a primary and this is a secondary. Okay? But we're kind of switching it up. We're going to make this the primary because we're stepping it up. It doesn't matter. I'll leave it like that. But just so you know, now this is the 240 volt side, right? Should put that a little better. So this is the 240 volt side. And the 575 volt side is multiple taps. And I'll show you guys when we go and look at it for real. Okay, so let's start with the easy configuration. So your incoming phases from my phase converter, right? I shouldn't say phases. I should say legs. Phases exist between the legs, right? Leg A and leg B, the phase is in, I can't do sign language, it's in the middle, right? Finger A, finger B, the magic marker is the phase between them, okay? So I'm going to misspeak because I'm used to saying it wrong. So this is leg A, leg B, and the manufactured leg from the phase converter is C. And it really doesn't matter, but I'm just letting you know that the manufactured leg is C. So A and B are 240 coming in from the power company. It's center tapped at the pole. Don't worry about that because we don't care. and then you have C. So A, B, and C with the circle are incoming power. So only pay attention for now. I'm powering up 3 coils, 3 transformers. The primary 1, 2, and 3. So all these transformers, it's actually the secondary coil, but the coil that's supposed to be 240 volts is 240 volts on all of these guys. So it's in a delta configuration. It's very simple. It's just like if this was one phase and 2 legs and it was 1 transformer, I'm feeding the transformer 240 volts like it's supposed to be, and that's all good and happy. I just happen to have, 3 legs and 3 phases and, 3 transformers total in a delta configuration. Nothing crazy about that. Nothing crazy. It's normal. Okay. So, the secondary, it's confusing because I'm running them backwards and I say primary and secondary. The other side of the transformer is capable of like 600 and some volts. It's like 600 volts. You got multiple taps. I mean, there's like 7 or 8 taps on there. 600 volts, one's like, 575, 550, 525, 480, 460, 440, 390, 380, 370. It's a whole bunch of taps. Very versatile transformer. But because I'm not using it, and I could take my load off this side, tie all the one sides together in a delta, and your output would be arrow A is your output, right? I could do that, but I said I'm going to make these wired for an auto transformer, not an isolation transformer, right? These lines of the iron core, that's the isolation, okay? That's the isolation, magnetically isolated from physical electricity. But what I'm doing is, see this wire here? See that wire there? See that wire there? That's a jumper. I'm jumping the primary to the secondary. So now it's not isolated anymore. It's an auto transformer, okay? So it's all connected together. And remember I was talking about the buck and the boost? Well, this is important. If you look, hopefully, not always is it labeled, but you can test it with a meter easy enough to measure the voltage. See, this coil has a beginning and an end, right? Beginning and an end, beginning and an end. Where it started the winding and where the winding is ended. So the start of the winding, a lot of times they got a dot, okay? There's a dot. The start of this coil is here. The end is here. There's the dot. The start of this coil is here. The end is there. What I'm doing is I'm connecting the end of one coil to the start of the other, right? I'm connecting start, end, right? I'm keeping the windings the same direction, right? If I went start to start, not end to start, if I went start to start, that would be a bucking situation where I'd get less voltage reading out of the other side. I would reduce the voltage if I bucked, but because that's if you change the direction of the windings. I'm keeping the direction of the windings the same. I'm just going to make this up and call it clockwise. Clockwise in the primary, clockwise in the secondary. So it's boosting. It's making the voltage boosted. So it's an auto transformer configuration running in a boosted orientation, right? So everything I do is going to be boosted up because my winding orientation is in the same direction. Hope that makes sense. Okay. So now, like I said, my current source is, leg A, B, and C with phases existing, A, B, and C between it. And the output is the arrow to A. That's the output. it's an arrow that looks like it's going outward. I didn't know how to label it, but so this is coming out A. So you have your, I'm going to call this the primary, energizing the transformer. It's magnetically coming to the other coil here, because that's what transformers do, and it's boosting it up, and because it's tapped, it's an auto transformer. So I'm tapping it higher than the original input. So I've got an output here of A, and an output here of B, and an output here of C. So I'm taking the output A, the output B, and the output C, and it's 575 volts, and I'm going to my grinder, going to the grinder, going to the control cabinet, going to the motor, because the whole thing is 575. And people are crazy with the grounds. So in reality, this 240 volts, right, you know, it's coming up here and it's grounded in the middle, right? It's a center tapped 240 is what the power company has at the pole. So at the pole, residential transformer service is center tapped to 120, right? It's 240 center tapped to 120, and that 120 in the middle, that center tap, that's ground. That's the symbol for ground. Maybe I didn't draw it very well, you know. Whatever, that looks worse. It looks like a Christmas tree. That's the symbol for ground. So if your A leg shorts to ground, it blows the breaker. If your B leg shorts to ground, it blows the breaker. With your rotary phase converter, a rotary phase converter is a motor, so instead of a transformer drawn in delta here, it's the same thing, except the motor rotates. It spins. It's got a spinning rotor. The transformer does not, obviously, but it's the same 3 coils. If something shorts out in your rotary converter to ground, trips the breaker. Because this is not an isolation transformer, I mean it was, but because this jumper leg here, jumper is the primary to the secondary, actually vice versa, but jumps the one coil to the next, it's no longer isolated, right? It's not a separately derived power supply. So any of these, you know, high voltage legs, output B, or output C, if they short to ground, it's going to blow the breaker, right? So if people are worried, hyper worried about safety and electrical code compliance, and I get it, right? I get it. You want to burn the house down, don't want the insurance company to deny your claim if something happens, don't want the lawyers chasing you, whatever. This is going to blow. I mean, there's multiple circuit breakers in a phase converter system. And there's multiple fuses, like most machines have three fuses on the input. They have fuses on the control transformers. Because this is no longer an isolation transformer, I mean, people are saying, oh, you got to use a Y-connected transformer because then you can ground the center point and have a new ground because you're inventing a new power source because it's an isolation transformer. This is not. Right? So don't worry about being delta. It's grounded at the pole. It's grounded multiple ways. So essentially, with a phase converter setup, your primary transformer at the pole is center tapped grounded. And this is kind of like center tapped delta. It's kind of how it is. It's not exactly that, but it acts like that. It certainly isn't Y. There's no star point. There's nothing Y about this or what's at your pole or nothing. Not. So consider it single phase is center tapped. People call it split phase. It's still one phase. It's not split. There's no phase angle derivation really. I mean, you could put a center tap transformer on an oscilloscope and you could see some physical time offset, but there's no rotational aspect to it, okay? All right. Hope you guys appreciated a little bit of what I'm saying. This is not exactly like I've shown it in any textbook or anything I found on the internet, but it's just taking a concept of a single phase auto transformer. Wiring an isolation transformer is an auto transformer, and wiring it in the buck mode as opposed to the wiring it in the boost mode as opposed to the buck mode. That's all it is. And just because delta preserves the voltage, you know, I can use 3 of them at the 240 designated voltage without any issue. None of this Y stuff. It's not complicated. It just jacks your voltages, and that's fine, but you gotta compensate for, you know, other parts of your system have to be spec'd for the Y voltage. Okay, you like that? I like that. Let's go take a look at the actual transformer box that I built, and you can put engineering theory to actual reality.